Welcome, everyone. We're ready to start. Welcome to this course on TCP-IP. My name is Jean-Yves Le Boudec, and I'll be your lecturer for this term. This is a practical course. There's a lot of labs, so we have a large group of TAs that I will introduce now. Our head TA, the one who's responsible for all organizations of the labs, is Roman Rudnik. And he will be assisted by Ehsan. Ehsan is the cameraman in the back. These lectures are taped. You will find on Moodle all the links to view the lectures if you missed one or if you want to see it again. Ehsan. And we have Arpan. Elena, who is not here today because she's writing a proposal. Jagdish was not here today because he's busy with his startup. Tong and Marguerite. So those are the people who will help you in the lab. So you will see them tomorrow in the class to assist with the first lab. So this course is about computer networking. There is no specific requirement other than the general requirements for EPFL master level courses. It's a course that will have a lot to do with practical. So you will have to be familiar with the computer and not afraid of using the computer, and be ready to spend a lot of time in the labs debugging things. That's the practice of computer networking. Computer networking is, like many things in software, and it's primarily software in this course, and like many things in software, is simple, made of simple things, but there are zillions of simple things. So the complexity comes not from a few big complicated things like Fourier transform, that's complicated, how do you know what it is? We don't have things like this, but there are lots of small things. One dilemma when teaching such a course is how to teach all those complicated little things. Fortunately, it's possible. The wrong course would be a 16-credit course where I would teach you all the details of all the protocols of computer networking. But this would not be good. This encyclopedic version would not be very interesting. Chances are you would forget most of it anyhow. The approach we will use, that many teachers use for such courses, is what we call the rake approach. So we have to do a balance between breadth and depth. If we give a course where we cover all topics of TCP/IP, we will be very shallow. If we cover a few topics, we will be very deep. Now, we have only limited time budget and credit budget, so what do we do? And the idea is to go deep into a number of selected topics. Those are the ones that you will do in the labs. And the hope, and you have to trust me and the experience of other people like me, is that by choosing specifically those labs, anything else that you have not done will be in the convex set of what we have done. So it will be easy for you to imagine what it would be based on the experience you will have gained on going deeply into a few things. If you don't go deeply into a few selected topics, you are likely to miss what TCP/IP networking really is about. But we need also a breadth. We need to be aware of the global picture. Another way to tackle this complexity is to separate two questions, what and how. What means, what is this thing doing? And very often associated with what is this thing doing is, why was it invented? Which problem is it solving? This is usually very simple and very fast. Then, how does it do it? For example, we will see that TCP is a protocol for providing reliability. So the problem, one of the problems that TCP solves is packets can be lost, and we need somehow to recover the lost packets. Understanding that is easy. And then you can easily imagine how you would recover lost packets. And probably your imagination will be very close to what TCP really does. Now, the how is typically very complicated, and this is what we will do in the labs. But very often, there is no rocket science behind what is done. Most of the how is the thing you would imagine. So there's no much point remembering it. So one way of compressing information in a very efficient and intelligent way is to know the what, trust your imagination for the how, compare it with what really happens, how it is really done, and then learn the difference. If there's a wow, if there's, oh, they do it in this way, then you've learned something. That's not something you have imagined. If it is, oh yeah, that's how I would have done it, then there's nothing to remember. So that's one way of managing this complexity. Very often, we will use, you will probably use Wikipedia. Wikipedia is a good resource for networking because it's typically done by people who are like me or others who are active in networking. But one of the side effects of Wikipedia is that it tries to cover everything and agree with all different opinions. So it tends to be very verbose and explain the how in very much detail. Not all, but many entries do that. So when you will go to Wikipedia to learn about things, try to separate inside Wikipedia the what from the how. Normally it's done at the beginning of a Wikipedia entry, the what, and the how at the end, but sometimes it's not fully separated. Right? This is similar to using a graphical user interface, a Macintosh, versus the command line in the Macintosh or Unix machines. Doing things, once you know that you have to do something, you find with the menu how to do it, and you don't need to remember how to do it. But if you use the command line, you may need to remember lots of things. In this course, in the labs, unfortunately, very often we will have to use the command line, so the how will be complicated. This is how the course is organized. We are in the lecture room today. Every Thursday, we'll do a lecture. Every Friday is a lab session and a quiz every other Friday. So the lab session is done on your own machine with the exception of one lab. What happens on Friday is that in the room you have TAs who are helping you with your questions, but you can do the lab anywhere, anytime. Just be on time for returning the lab assignment, but you can do it anywhere, anytime. In the past years, we had a request for an extra lab session that was particularly useful for Tong. Yes, thank you, Tong. There's a bug here. It's until 1 o'clock. So Tsong is worried about having to TA until 2 o'clock. No, that's a bug. I will correct that in the final version. It's until 2 o'clock. There's an overflow session that was asked in the past year on Tuesday. That's useful particularly at the beginning for those of you who perhaps don't come from computer science and might take more time. Then we will do this overflow session at least as long as there is a request for it. The quiz is every other Friday, so not tomorrow, but next week there will be one. It's mandatory. It's part of the final grade, as I will explain in a minute. If there are questions, feel free to interrupt now or at any time. We will use primarily the copy of the slides that I'm showing here as the lecture note. If you need more information, I use as a reference one textbook, which is freely available. That's by Olivier Bonaventure in Belgium. For some other parts, there will be some specific notes, but we'll come to that later. A few words about the labs. I give the microphone to Roman.
Okay, so I will give a brief introduction in the organization of the labs and the environment that you will have during lab sessions. So you will have 7 labs in total, so which are mandatory and graded. So as the professor said, the main slot will be on Fridays from 11:15 to 1. Additionally, we have a slot for you on Tuesdays from 4 to 6 in INF 019. Which is the internet workshop room. We allow you to collaborate with groups of 2 people, so you can find a teammate to do the labs together. And also, so all labs will be uploaded on Moodle. and please fill it as the PDF inside. So don't write any other documents. It's not needed. You will have 2 weeks per lab, except lab 0. So usually you upload the labs on Wednesday in the evening, and you also should upload the lab before the next lecture on Wednesday. So in order to emulate a network, we use a mininet, which has a Python-based API. So the virtual machine with the mininet is already on Moodle. You can download it and start playing with it. Also, some labs will require IPv6 IP addresses, which EPFL doesn't provide, but we have it in INF 019. So there is an access point LCA2 TCP-IP labs Wi-Fi that gives you IPv6. So, for example, lab 0 will need the IPv6. The password for this access point will be given to you in the description of the lab 0. So you will need access to INF 019 because, for example, lab 2 is hardware lab, so you have to play a bit with the real hardware. For that, please go to the Moodle and fill the lab rules agreement. I saw that some of you already did. Good job. Please do it before the next Thursday, so then you will have access to INF 019 using your CamiPro. So please keep material in lab in a good state because we have equipment there for you, and keep it clean. So respect the EPFL rules. So a couple of words about first 2 labs, which are very important. So lab 0 is introductory lab. So there you will have some basics about IPv6 and IPv4. And this lab is different from other labs because here you will have only 1 week. So you should upload it next Wednesday before night. So pay attention to it. Also, lab 1 is introduction and the background for the mininet. And so there you will have all details that you will use in the future labs. So please be very careful with this lab, otherwise you will not be able to do other labs. So we know that some of the students have no background in TCP-IP, so that's why you maybe will have to spend more time, and that's why we have to use the time slot. Also, each lab except lab 6 will have an optional research exercise for you that you can do if you want to have extra bonus points for the lab. So TA team here is to help you, so you can ask the questions, but please be as much as dependent as you can. So try to use Google and Stack Overflow because plenty of problems that you will face are already explained there very well. For the report, in each question, please don't write a full summary about what you do. 2 sentences is more than enough. And please don't cheat. It's very easy to recognize, and you'll be penalized for that. So in order to communicate with us, so usually all important information is on Moodle. However, now this year we will use the Slack channels for the discussion of the labs and lectures, content of the lectures. So we have 1 Slack channel per lab and 1 channel for the general questions about the course. So we already created the workspace on Slack. So all of you should receive an email till tomorrow. So please, if some of you will not receive this email, let me know. So then you'll be able to register in the Slack. All information about the Slack is also on Moodle. So some of you who haven't used it, please take a look. About the rules, how we're going to communicate. You can ask questions there, but please, first when you ask a question, check if someone of you already not asked it. Let's not create a mess in Slack. You can also answer the questions of other students because we know that some of you are already very familiar with the material. And for that, you will be able to get the bonus. So if you find the answer of other students useful, you can put thumb up. And 2 students with the most big number of thumb ups will give some bonus at the end. So it's 0 to 25 points. So in this way, we want to have a more communication between the students. So enjoy. That's all from my side. Yes.
So I have a question. You have mentioned a few software tools like
Yes.
Net. Will I have any problems if I'm using Linux or Windows or Mac OS?
Well,
Specific or not?
oh, no, usually not, but we have a virtual machine for you with TCP, with this Minet already installed. It's on Moodle.
Okay.
It will be explained in Lab 1 how to set up it, so shouldn't be any problems with it. Other questions? Okay.
I mentioned that there will be tests. The idea of the tests is to make sure you work continuously and before the labs also, so that because there's a logic between the course and the labs, so you should study the lecture before starting the labs. And to help you make sure you do, then we do tests every other week. Only the 5 best out of 7 are used for grading, so you have two jokers, which means also if you have a dentist appointment or you have to go to hospital or see your mother-in-law at one of the Fridays, then there's no excuse, you will simply skip up to 2. During the tests, like at the exam, there is no document allowed, right? Just a pencil, and then you'll have to tick boxes. No documents allowed. Of course, we will not ask questions that are specific about what is in the 24th bit of this address or things like this. The idea of having no document is to force you to learn the things that I think you should learn. You can look at the test of the past 2 years. They're online. You can train yourself with the tests using Google Forms, so you can try them and you will have an idea of what is awaiting you. I will also sometimes use SpeakUp, like now. SpeakUp is a tool to poll you, so where I ask question, I would like to have your opinion. Many of you have used it. If you have not used it, you can go to the website that is given there. There's an app that you can download, or you can also open a web browser and go to the address that they give. And as a test, I'm interested in knowing what is the background of all of you. So this poll should be open, and I invite you now to test your SpeakUp. SpeakUp allows you to send messages in class anonymously, but I have to warn you, you have to do it ethically. You cannot use it to abuse other people or do things that are illegal to do anywhere, right? If that happens, we can make SpeakUp non-anonymous. Right? The exam is also, which is in the exam session, is also closed book. No document is allowed. But at the exam, you will have what I call the exam booklet, which is a set of slides that give you some technical information, and that is already available on Moodle, so you can have a look at it, and you will know what you don't need to learn by heart. Everything that is not in the exam booklet has to be in your head for the exam. The grading is given here, so it's a complicated formula that I'll let you discover, but the main thing is that the theory, and so the theory is made of 40% of the tests and 60% of the final exam. And the lab grade, which is given here, is the average of all labs with a weight of 1/2 for the first lab, which is shorter than the other ones, where we add the research exercise bonus, which is, as mentioned by Roman, an optional question. We understand that some of you are already familiar with some of the software techniques that we use in the labs. Then they may want to do more. So you can take those optional questions, which are small research questions. If you're interested in the topic of a given lab, you can take it and it can give you bonus. And we will give you feedback. And there's also a small bonus for the social influence bonus that was mentioned by Roman. Slack channel feedback that you give. So the theory and where is my formula? The final grade is the mean of the theory and the practice, the lab and the theory, because this is really what TCP is about. There is some theory and a lot of labs, so ideally the lab should count more, but it's harder to have a true grading system for labs, so the average is the same. And the twist here is we take the harmonic mean of the two. Does anybody know what the harmonic mean is? Yes? It is? It penalizes lower grades, exactly. So we take 1 over the grade between 1 and 6. We take the sum, the mean of the inverse, and we inverse again, right? Which is like a contorted way of saying if you fail miserably at the theoretical grade, if you have 1 out of 6 as the theoretical grade, it's impossible to succeed. So you cannot make up by the labs, and vice versa. So, and if you are about the same at the 2, it's like the standard mean. This is the roadmap. We will start today with an overview of TCP/IP. So the course will be in 2 rounds. In the first round, today, we will cover everything. And then the second round will take the rest of the course. We need that because to do practical labs, we need already to be able to do things with the machine. So we need to have a complete idea of at least a bit of everything, which we will do very quickly today. And then you have the other modules as they are explained here. There is 1 lab per module, except the last one, because the theory always comes before the lab. The last week, there will also be no lab session. Questions on this organization stuff? If there is no question, then we move on to the technical parts. And as promised, we will go very quickly today through an entire view of what I call the TCP/IP architecture. The first remarkable thing about TCP/IP is that it is layered. So the word layer is used. A layer is something that we find in other systems. In software in general, we call that a module. To write good software, you have to make it modular. The idea of TCP/IP here is the same. We have to break the functions into blocks that fit together such that every function is smaller. Why we call it layer is that when you do communication, there is something special that you don't do one module that is alone. This module is always communicating with another one. So layers mean simply modules that communicate with each other, that are peers. Depending on the textbook you will read, you will find 7 layers or 9 or 5. It's largely irrelevant and everybody can argue what they are, but it's usually well understood that there are those 5 that I'm showing here. The application layer itself tends to become the bigger one and is split into subpart. But roughly speaking, we can divide them into those 3 groups. The physical layer is about transforming bits into physical things, like most of the time radio waves that are in the visible light for optical fiber, or radio waves on non-visible radio waves in general. That's not the topic of this course. This is the focus on the digital communication course. Then we have 2 layers in green here called the network and the MAC layer. They have to do with connecting systems together. Connecting at a low level, making sure information can go from one machine to the next. Then the blue layers are the software layers. The blue layers are about connecting applications together. Why there are transport and application, we'll see that in a second. So what we will do today is we will go very briefly through the 4 layers, and we'll say a few things about the physical layer too, that will allow us to get started. The application layer is the most visible and interesting part of the internet. We'll say a few words about it, in particular about things like quick and application layer frameworks, but perhaps in its simplistic, most simple form, when you access the web, ignoring security, we'll come back to security a bit later, what you do is you have a web browser that communicates with a web server. So for each of those two machines, they have the illusion that there are only two machines. When you click on something, the web client sends a request to a web server. At this level, there is what is called a protocol. The protocol is the rules that govern the interaction of two entities, two or more entities that are at the same level. So a web client and a web server use a web protocol. The web protocol is called HTTP. Of course, application layer is the most interesting thing, but it's not the topic of this course, as I said. The transport layer, which is less visible, but is one that we will cover in detail, is serving the application layer in a generic way. Whenever you write an application over a network, you have to do things like transform a block of data into the things that a network understands. A network understands things like IP packets that we will discuss in detail. So this transformation has to be done by an application. Instead of having every application do it, we do it once for all, and we call this the application layer. The first thing to remember in TCP-IP is that there are, in fact, two transport layers, TCP and UDP. TCP-IP is a misnomer. TCP-IP means the entire set of protocols of the internet. And the most spectacular ones are two protocols called TCP and IP. So here is TCP, that is coming. TCP is what we call reliable. Reliable means if I send one piece of information from A to B, it may be, unfortunately, that some elements of that information are lost. As we will see, that's one of the key central and recurrent problems in the internet. You can never guarantee that a packet is received without error. In order to guarantee this, you need to do some work. This work is done by TCP. TCP will do things like put numbers in packets and count and ask the destination to send an acknowledgement that which number have correctly arrived. And if it sees that some numbers are missing, it will retransmit it. So this is what TCP does. TCP does it for you as an application developer, so that if you use TCP, you don't have to worry about missing packets. You just have to use TCP, send your data. If anything goes wrong, it will be handled by TCP. TCP has one peculiarity. It is what we call a stream service. So, second thing to remember about TCP, it's reliable, but, there is a big but, it is not behaving the way we would expect it. The way we would expect it is, I have a chunk of data to send, an image, for example, a JPEG file. I would like to use a TCP interface, put the image into this interface, forget about it, and have it sent to the other end. Which is more or less what happens, with a small difference. What TCP delivers is bytes of information. So your JPEG file will arrive at the other end as a stream of bytes. So the application program that reads this JPEG file will need to pull the bytes one by one, recognize when it's the end of the JPEG file, because perhaps it's not just one image but two. So the second one will not, TCP will not tell you that's the end of the message. Here comes another message. No, TCP will give you a stream of bytes. Second thing to remember about TCP. This means, of course, that the application layer needs to put some format into the messages that it is sending. If I send you an image, there will be what is called a MIME header that says when the image starts and how it is encoded. And when I read the bytes given by TCP, I have to analyze those headers. And if the header tells me the next 10,000 bytes are the image, then I count 10,000. And when this is gone, I know that the image is over. So this is TCP. UDP is another version of the transport layer that is different. So an application has to use TCP or UDP, but both ends have to agree. They both use TCP or they both use UDP. If you use UDP, you don't get reliability. So UDP is a very shallow transport layer. In fact, it does practically nothing. We'll see in detail it does a few things. But at this first round of approximation, it does nothing except it guarantees you that a message is delivered as a message. So it doesn't have the streaming problem of TCP. If I send an image using UDP, I send it in one or several packets. Then when I receive, the application program asks UDP, give me what you have received, it will send the image. Or nothing if a packet has been lost. So UDP will not deliver anything if it's lost, but if it delivers something, it delivers what was sent as one message. So we say it's datagram. We say it's a datagram service. Datagram means this, it sends one message as a message, whereas TCP sends a streaming service. But UDP is not reliable. Why do we have both? Why don't we always use TCP? Well, we'll come back to that. One of the reasons is TCP has a cost associated with it. In order to be reliable, it needs to do what is called a handshake. So before sending 1 byte of information with TCP, you need to do a few things before to put in place some synchronization data, some data that exists at both ends. So if you have to send very short things that fit in one message only, you typically don't use TCP. We'll come back to that. We continue going down through the layers. The next layer below is the network layer. So the network layer is solving the problem that's illustrated here. You want to interconnect the millions or hundreds of millions or billions of devices in the world. How do you connect them? Well, you can pull radio links or cable between all of them, but of course this is not efficient. It's impossible. So how does it do it? It uses what is called intermediate systems, like the post office does. So the model of the internet is that of the post office. You put your letter into a mailbox. A postman comes and puts the mailbox to the next post office switching center that analyzes the destination address, sends it to other switching centers. That's exactly how the internet works. Though at the beginning, the internet, what was the very first versions of the internet, did not use this system. They used what is called store and forward. With store and forward, at the beginning of the internet, the routers were computers, and the computers were expensive, rare things. On a campus like EPFL, there were 2 or 3 computers at all for the entire computer. So one of the computers was used as a switching center. So if I would send a message from A to B, the message is sent to the next computer that sends it to a next switching center and to the final destination. So the entire message is sent from place to place. At that time, entire messages were not very large, but we can wonder what would happen if we do that today. Well, today, what we do is to use packet switching that was invented by a French guy in 1974. And the key idea, that's the one that is still dominant everywhere today, is to break any piece of information into standard containers that have a maximum size. Now, the maximum size depends on the technology, but by default in the internet, it's around 1,000 bytes. Up 12,000 bytes is 1,200 bytes is the most common size. And those are called packets or datagram. If we use this analogy, if I send a mail over such a network, the mail is broken into chunks, into packets that reach the next intermediate system, which is now the mail server. And now the mail server recreates the entire message from all the different packets and send it perhaps to another intermediate mail server that sends it perhaps to the final destination. That's a typical case of what happens when we use email. We have our own mail server, the destination mail server, and between those mail servers we use IP, the network layer, and between the client and the mail server we use IPs. Did you observe anything specific about those messages? How they were sent? Yes? Some took different paths, exactly. That may happen, although we try not to have that too often, but every packet in the internet is like a postcard, is an independent entity. So one of the functions of the transport layer is to hide this fact from the application layer. So with TCP, we'll transform things that come into packets that may come in different paths. If they come in different paths, they may come possibly in different order. It's possible that packet 3 arrives before packet 2. TCP will hide all that stuff away from the application layer programmer and give the illusion that I have a fixed pipe that is sending bytes. Why do we think that we moved historically in 1974 from store and forward to packet switching? What is the benefit? Speak up. And you can see the results on your device. The majority thinks that it reduces the buffers required in the routers, which is the correct answer. So the possible things we may think of is that it reduces the delay and the storage required in routers. This is explained on this graph here. Here I'm showing what we call a time-space diagram, something that's very useful to reason about timings in computer networks. On the vertical axis is time. On the horizontal axis is space. So I'm showing a packet going from one place to the other. One remarkable thing here is that the lines are not horizontal, which simply means that the speed of light or the speed of propagation of signals is not infinite. Although everything is very fast, the computers are also very fast. They do computations in nanoseconds, and it takes nanoseconds to get through a few meters. So the propagation time does play a role here. If I send an entire message into a system that needs to forward it, like I do if I go through a mail server, the mail server has to keep the entire message until it forwards it again, which has two side effects. One, delay. Before being able to send it further, we need to receive the entire message. If the message is a video of 1 gigabyte, it will take some time. And another side effect is the storage required of the intermediate system. The intermediate system needs to store huge amounts of things. So in order to avoid that, we do packet switching. That's the motivation. Packet switching does not increase the capacity. We will see, in fact, that it might even slightly reduce it when we'll talk about the transport layer. The main motivation is this one, to have what we call cut-through. This is what the internet is doing today. Here is a vision, snapshot of a few years ago of the EPFL network, the IP network of EPFL. The cheese boxes like this one are the classical drawings for routers. And you see lines, the green and the red lines that are showing interconnections between routers. Those are typically switches. We'll talk about switches a bit later. But for the vision of IP, we can think of them as lines connecting routers. And you see numbers. Those numbers are addresses. In order to use this system of packet switching, we need to have addresses. It's like the postcard system. When I send a postcard to somebody, I need to give the street address and the postal code. So the equivalent of that is called an IP address. The IP addresses, you see them marked as 128, 178, 71, 22. Those are, in fact, strings of bits. An IP address, shown here, is 32 bits. And as explained here, it's written by groups of 8 bits. So a group of 8 bits, like 128, is the decimal representation of a number that is occupying 8 bits. If today you have to write bits in a human-readable format, what do you typically do? You use hexadecimal numbers. Right? One hexadecimal number represents 4 bits. When this was done in 1974, people were not so familiar with hexadecimal numbers, or they thought system managers would not like them, so they used decimal notation instead, which is a bit awkward because the number of digits is not the same. So any number here is a string of 8-bit, and the max number that you can see here corresponds to this bit, the string of 8 of all ones, which correspond to 255. So it's a group of 4 numbers that must be between 0 and 255. The addresses I've shown are the old address types. They are called IPv4. The current numbering system is IPv6. So there has been in total 6 versions of the Internet protocol. Versions 1, 2, 3 were experimental and were very quickly deprecated. Version 4 was the first one that went public. Version 5 is an accident. It is not at all IP. It's the protocol called ST2. And the next version is IPv6, which is probably the final one. Probably for the centuries to go, we will stay with IPv6. Why will we? Simply because the size of the address space is what matters. If you have 32 bits, that means you can address how many devices? Yes? 2 to the 32, and that's how many? 4 billions. 4 billions. So 4 billions was huge when this was done. Remember, there were a few computers per university, so 4 billion was an astronomical number. But now that everybody has several devices, and we are several billions on Earth, perhaps 10 billion soon, so that is not sufficient. So the IPv4 address space is not sufficient, so it has been increased to 128. So we multiply by 4 the address space, which means we put this to the power 4. And then this number is truly astronomical. We will never, never exhaust this quantity. Yes?
People only back that you do back in the early days of IPv4. So maybe 20 or 50 years, somebody would give you that course and saying, oh, they were sure IPv6 would last forever. How do we know that this exponential trend is not to continue?
Well, it has to do with the population of Earth, right? We will not grow into billions into 10 to the power 1. So the number of bits of an IPv6 address is 128, right? So it's 10 to the power 36 or 37. So even if you give zillions of IP devices to everyone on Earth, you can still give an address to each other. Of course, I don't have a theorem and a proof that says this will stay forever. Perhaps I'm wrong, but it's very, very likely that it will take a huge time, an astronomical time, to exhaust this. IPv6 addresses are written using hexadecimal numbers. So here are examples. An EPFL IPv6 address is 2001. I say 2001, it's formally incorrect. It's not the number 2001, it is 2001, but it's an hexadecimal number. But it's 2001 because it was standardized in year 2001. 626.18 is a prefix, that is the prefix allocated to EPFL. Right? So if you see anywhere in the world 2001 626.18, in fact it's EPFL. And 1A6 is a prefix allocated to a part of EPFL, as I will explain in a minute. Right now, what we need to know about IPv6 and IPv4 is that they are incompatible. If you have a device that speaks IPv4, if you send an IPv4 packet to a machine that runs only IPv6, it will not understand it, will not work.